Okay, so I want to talk about the fact that there are three ways to write a vector. The first way is if we know the initial point and the terminal point. For example, if we're given an initial point of 1, 2, and a terminal point of -3, 5, then to write the vector in component form, we simply look at the difference in the x component, and that's going to be terminal minus initial, and the difference in the y components, again, terminal minus initial. And so this gives us the vector having components -4 and +3. And so if you look at a picture of what's happening here, we had a vector, let's see, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay, we had an initial we had a vector that had its initial point at the ordered pair 1, 2, and its terminal point at the ordered pair -3, 5, which puts it about right here. And so what we want to do is we want to pick up that vector and put it to where its initial point is at the origin. When we do so, what we need to make sure of is that the distance in the x direction stays the same and the distance in the y direction stays the same, and that angle stays the same. So all we have to do then is determine what the differences in the x coordinates are for my x component and the difference between what the y coordinates are for my y component. And so that in component form, my new vector has the coordinates -4, 3, which puts it about right here. So what we should get is a vector that has the same direction and the same magnitude, but we're just picking it up and moving it. The second way we have to write a vector is if we know its magnitude and a unit vector in the same direction. And this came from the way it is we normalize that vector. To turn a vector into a normal vector, remember we use the formula that u, and we do put a cap on that. A unit vector in the direction of a vector v would be the same as the vector v divided by the magnitude of the vector v. Since magnitude is just a number, I can multiply both sides by the magnitude, and I get that v will be the magnitude of v times a unit vector in that direction. And so what that means is, if you look at this graphically, if I know a unit vector, and a unit vector has a length of exactly 1, and so if I know this unit vector, say here, and it's in the direction that I want it to be, then to find another vector in that direction with a given magnitude, all I have to do is to multiply that vector times whatever I need. So for example, this has a magnitude of 1. If I want a vector that looks exactly the same as that but has a magnitude of 3, I just come in here and multiply that by 3. And when I do, I get that vector, same vector, but it's elongated to 3. That only works if it's a unit vector, though, because that unit vector has a length of 1. If that unit vector had a length of 2, and I were to multiply it by the magnitude I want, which is 3, I'm going to get a vector of longer magnitude, that is a magnitude of 6. So it only works with unit vectors. Let's look at an example here. Let's write the vector v with magnitude of 2 in the direction of the vector u, or let's call it any other vector, let's call it w, having components 1/2 and square root of 3 over 2. Now, if W is a unit vector, and it's in the direction that we want, then all we have to do is multiply that by the magnitude we want. So before we get started, we need to check to see if W is a unit vector. How do we tell if something's a unit vector? Well, we consider its magnitude, because the magnitude of a unit vector has to be equal to 1. And the magnitude of any vector is the square root of each of the components squared. So it's the square root of 1/2 squared plus the square root of 3 over 2 squared. And for fractions, we simply square the top, square the bottom. So this is going to be the square root of 1/4 plus 3/4. So it looks like the square root of 1, which is 1. And because we have a unit vector now, to find our vector v, we simply multiply the magnitude of v times our unit vector w. So, sorry for going across the page here, but I'm out of room. It's going to look like 2 times the vector having components 1/2, square root of 3 over 2, or the vector having components multiplying that 2 through 1 square root of 3. Now remember, that only works if you have a unit vector. Let's suppose I take a problem and let's write v having a magnitude of 2 in the direction of the vector w, which has components 1, 1. Now remember, that formula only works if what you have is a unit vector. Well, let's determine if we have a unit vector, and we do that by taking the magnitude of w. Well, the magnitude of w is the square root of each of the components squared, so it's the square root of 1 squared plus 1 squared, which is the square root of 2. This is not a unit vector. And so even though it's in the same direction as the vector we want, it is not a unit vector. So what is it we need to do? So let's turn it into a unit vector. And we can turn any vector into a unit vector by simply multiplying that vector by 1 over its magnitude. So in other words, we will take our vector w, which has components 1, 1, and multiply it by 1 over its magnitude, which is the square root of 2. So that a unit vector in the direction of the vector we're looking for will have components 1 over the square root of 2, 1 over the square root of 2. And now that I have a unit vector in the right direction, my vector v is going to be the magnitude of my vector times the unit vector in that direction, which is going to be the vector that looks like 2 times the vector having components 1 over the square root of 2, 1 over the square root of 2. And then I believe when you multiply that through and then rationalize the denominator, you should get a vector having components square root of 2, square root of 2. Okay, and we have one more way to write a vector, and the third way to write a vector is if we know its magnitude and the angle it makes with the positive x-axis. And the reason for this is as follows. If I have some vector here in component form, I will call it my vector v. Then I know that the terminal point, and by the way, let's give v components of v1 and v2. Then the terminal point is located at the ordered pair v1, v2. And folks, there is a difference here. And be aware of that. Let me give you just a little bit of a caveat to this example here. This vector that I've drawn has components v1, v2, but that simply means that I'm starting out with a vector that has its initial point at the origin and its terminal point at the ordered pair v1, v2. And so what that means, if I drop this perpendicular here, is that to get to that point, I'm going to go over whatever this amount v1 is, and I'm going to come up this amount v2. Let's let theta be the angle that the vector makes with the positive x-axis. Then I know that the cosine of theta will be the length of the opposite side, which is v1, times the length of the hypotenuse, which is the magnitude of v. Likewise, the sine of that angle will be the length of the opposite side, which is v2, divided by the length of the hypotenuse, which is the magnitude of v. Then solving these for v1 and v2, I get that v1 is equal to the magnitude of v times the cosine of theta, and v2 is equal to the magnitude of v times the sine of theta. And that gave us the ability then to write a vector as long as we know its magnitude and the angle that it makes with the positive x-axis. So let's look at an example. Okay, so in this example, let's find the vector v with magnitude equal to 3 if it makes a 45-degree angle with the positive x-axis. All right, so the vector v then is going to be equal to the magnitude of v times the cosine of theta for the first component and the magnitude of v times the sine of theta for the second component. And you will need to use a unit circle on this because I don't want your decimals. So the only time we can do decimals is in a word problem. This is not a word problem. Word problems are the airplane problems you're going to see at the end of this section and the skiers problem. So we're going to take the magnitude, which is 3, times the cosine of a 45-degree angle, which is the square root of 2 over 2, and then the magnitude of v, which is 3, times the sine of that, which is the square root of 2 over 2. So we simply get the vector having components 3 square root of 2 over 2, 3 square root of 2 over 2. On this last page, if I write something like this, I am talking about an ordered pair. If I write this way, I am talking about a vector in component form. If I put a number inside of the single lines going down it, I am talking about an absolute value. If I put a vector inside of something with the lines going down it, I am talking about its magnitude. So be very careful with your notation on this. All right,